Okay, this tells me I have to use the kV. This tells me it has to have a K involved here. That it doesn't go completely to that direction at that particular point. Okay, so the kV, which we said is 2.22 times 10 to the negative 11, is equal to, well, let's go back over here. Oh, we said the concentration of the weak base is 0.25 moles per liter. So it's going to start at 0.25 moles per liter. We're going to lose X here, going to gain X here, it's going to gain X here. So that's going to give us X squared over 0.25 minus X. Now we got to turn that into a quadratic equation, multiply by the denominator, add negative X squared, re-add everything, blah, 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 what we've done a bajillion times already. And we should get negative X squared minus 2.2 times 10 to the negative 11X plus, and a quarter of 22 is 5.5 times 10 to the negative 12 equals 0. Okay, so I'll turn on your calculators again for the 10 millionth time, get quad form going there. Got negative 1 for A, negative 2.2, E negative 11 for B, and 5.5 E negative 12 for C. And you get 2.35 times 10 to the negative 6 moles per liter. That is the concentration. But what does X represent? We have an X by the NaOH. This is a weak acid, it's immaterial. This is a strong base, it's a hydroxide. Hydroxide means base. So that is the concentration of your hydroxide. I'm dropping the Na because it's what we call a spectator ion. It has no effect. In fact, it's not really there because it's dissolved in water. And sodium ions are just floating around, whatever they're doing, just having a gay old time. Just wonderful. So now we are going to find the POH. Well, that is a hydroxide. Oh, probably should put that in the chart. 2.35 times 10 to the negative 6. So 2.35 times 10 to the negative 6. Now I put hydroxide, not strong base. I have to put hydroxide in because that is what's driving the pH. Okay, so now we take the, well, let's quickly review how we did that before. Because we did that in stage 4 of the strong acid, strong base. And what I mean by that is this: if I want pH, I can get POH here by taking the negative log of this quantity. And we know that pH and POH add up to what? You said 14, you are correct. And so 14 minus POH, which is 14 minus the negative log of 2.35 times 10 to the negative 6. And we can change this to plus a positive. So we take 14 plus the log of 2.35 times 10 to the negative 6. And we get, it would help if I took the log of that instead of just putting in 2.3335, blah, blah, blah. So let's insert my log that I forgot, and let's get a real answer. Now we get 8.37. And look, it's greater than 7, just like I said it would be, because you have a basic solution. So we put 8.37 into the chart. Okay, that's stage 3. There's only one part for stage 1, and there's only one part for stage 3. Stages 2 and 4 can have multiple parts. Sometimes they will, sometimes they won't, depends on how many parts I give you. Stage 4. Now I got 0.02 of the weak acid, I got 0.025 of the strong base. That is stage 4. So, get rid of that now. Alright, so now I have 0.025 of this. Now we have more base than acid, more strong base than we have weak acid. And the next statement you'll see happening here, so you lose all of that, you lose 0.02 here, and you gain 0.02 here. 0.005 moles of hydroxide and 0.02 moles of the conjugate or weak base. This is a strong base. This is a weak base. Yes, we have more moles of this, but very tiny amount actually breaks apart, associates. It's going to be way less than 0.005 moles of hydroxide to the point where it is insignificant. The weak base is insignificant. So, bye-bye. And we just focus on this. So we don't have a duality that we have to worry about here. We're just going to put in the 0.005 moles of hydroxide, go all the way back to the second point. 0.005 of hydroxide. Divide that by 0.09 and the 0.0556 moles per liter of hydroxide. Again, this is hydroxide, so we just take 14 plus, punch in the log, idiots, thank you very much, 0.0556, get 12.75. Remember, I want 2 decimal places in all of my pHs, not 3 sig figs, 2 decimal places, 12.75. Next one, we do one more, we got 0.02 and 0.03. This won't take very long to do. 0.02, 0.03. All of that is gone, subtract 0.02 here. I got 0.02 here. There's 0.01 moles of hydroxide. We really don't care about this right here. We'll focus on that. So put 0.01 moles of hydroxide into the chart. Divide that by 0.10 and we get 0.1 moles per liter of hydroxide. I know the answer to this. I don't have to punch this one out. This is going to be exactly 13, but I want 2 decimal places, so I'll put 13.00. That's how you do the weak acid strong base titration. A lot of moving parts. You might want to keep referring to this whole section right here. Last thing I want to do is show you how the graph is different from the strong acid strong base titration. And here's what we got. Now, again, I want to emphasize the differences between the strong acid, strong base, and weak acid, strong base titration. This is stage 1 for the weak acid, strong base. That is much higher than the 0.3 we had if we got the equivalent strength of strong acid. Stage 2 goes between the original pH of the dissolving of the acid to what we call the equivalence point. Here's second difference, the little jump right here, where before we were going like this. You can look at the other one. I don't want to mess it up too much, so because the important parts don't need to be missed. We called the equivalence point here, but we said that it was 8 point something something. I don't remember offhand, 3.3 or 3.0 or something like that. Well above the 7. Now, here's the other difference, the half equivalence point. We didn't care about that in the strong acid, strong base, because it really had no significance, but it does here. And one of the things that we could do for labs, we can find the actual Ka of a weak acid by titrating like we did, and then find the half equivalence point, because at the half equivalence point, what's the half equivalence point? That's the point at which the number of milliliters it took to get to the equivalence point is divided in 2. So this is the half the number of milliliters of the equivalence point, and we call this the half equivalence point. That right there, that pH right there is equivalent to the pKa. Remember, when I told you to divide or take the log of two numbers that are equal that are dividing, that's what happens. You don't have any extra acid or base in that buffer. It's even. And that means then that is going to be equivalent to your pKa, because the other part was equal to 0. Which is, and pKa again is called the negative log of Ka. So there's stage 2 right there. Okay. Stage 3 is the equivalence point, and the pH we said is greater than 7. And then after that, that's where they become identical. The two titrations are exactly the same above the stage 3. In stage 4, it's the same thing. Long videos, I'm sure there's at least 3 parts to this, but lots to go over. Hopefully you're going to take a little time to get through this. This is a tough section, this and the next, but if you get used to it, you're in really good shape. Practice problems. You have 2 titrations charts to make. Half